Great, so let's get started. So the plan for today is to really primarily talk about multitask learning, but then we'll also go over some of the basics of transfer learning as well. In multitask learning, we'll talk about the problem statement, we'll talk about model architectures, objectives, and optimization. We'll talk about some of the challenges of multitask learning, and then we'll go through a case study from a multitask YouTube recommendation system that was actually quite recent from a paper that was from last year. We'll also try to take a short break after the challenges between the case study, like a couple minutes, although if we're low on time, we might skip that. It depends on how many questions there are. And then lastly, the goals is by the end of the lecture, you should be able to kind of understand the key design decisions when building multitask learning systems, understand the differences between multitask learning and transfer learning, and also understand some of the basics of transfer learning. Cool, so that's for the plan for today. So first, some notation that I'll be using throughout the lecture and also likely in future lectures as well. So we'll be considering multitask learning with neural networks for the lecture today. And we'll use X to denote the input, Y to denote the output or the label. And this may be something, the input may be something like an image, for example, the image of a tiger. And then the output may be a probability distribution over what you think the label is, whether you think it's a tiger cat, a lynx, a cat, and so forth. Or the input might be something like the title of a paper. Maybe you want to know whether or not, given a title, you should review that paper. Maybe you don't like reviewing papers that are really long, and so you want to train a neural network to estimate what the length of the paper would be based off of the title of the paper. So the input could be things like images, text, really a wide range of unstructured inputs, and the output is typically something a little bit simpler, but is something more related to what you care about. We'll use theta to denote the parameters of the neural network. And then we'll denote the the function that this neural network represents as f parameterized theta of y given x. Cool, so that's kind of the basics. And if you were to do single task learning, such as predicting the label of an image, then we would typically assume that we have a data set of input-output pairs. And then we would formulate some loss function that may correspond to the negative log likelihood, such as a cross entropy loss or mean squared error, and then try to minimize this objective function and specifically search over the parameters data. And so your loss function might look something like this. And then typically you optimize this loss function with stochastic gradient descent or your other your favorite optimizer. Okay, so now let's revisit the question of what is a task, and this will allow us to set up the multitask learning problem. So, and we'll talk about this actually a little bit more formally than what we did last lecture. So we'll define a task as a set of three things, p of x, p of y given x, and the loss function. And in particular, these distributions P are representing essentially the data generating distributions. I is indexing the task. And each of these tasks will have a corresponding data set that is drawn from the data generating distributions. And typically you assume that you have a train set and a test set where you train on the train set and then during evaluation you evaluate on the test set. We'll also use DI as shorthand for dtrain I throughout the rest of this lecture, just to simplify some of the notation. Okay, so this is going to be our formal definition of a task. Now let's look at a few examples of what tasks might look like. So one version of a multitask learning problem would be multitask classification, where maybe you want to be able to classify different kinds of objects. And in this setting, the loss function is going to be the same across all of the tasks. It might be negative log likelihood or cross entropy loss or something. And some examples of this is maybe you want to be able to recognize different handwriting characters for different languages, and different languages will correspond to different tasks. Or maybe you want a spam filter, and different tasks will correspond to different users. And they're essentially, in both of these settings, the distribution over X and the distribution over Y given X are going to be different for different tasks, because different users have different kinds of emails, and also different languages write characters in different ways. But what will be kind of the same across tasks will be the loss function. So this is kind of one example of a multitask learning problem. Another example of a multitask learning problem is what's called multi-label learning. In this setting, the loss function and the distribution over X are going to be the same across tasks. And it's what is this distribution P of Y given X that's going to be different. So an example of this is trying to recognize different attributes of faces. So maybe one label corresponds to recognizing whether someone's wearing sunglasses or whether someone's wearing a hat, or another label is recognizing someone's eye color or something like that. So in this, basically the data set that you have, both the data generating distribution over X and also often the inputs X in your training data set are identical, but what's different is you have different labels. Okay, and then the kind of an example of scene understanding that actually comes up a lot is when you want to understand a scene or an image of a scene, you typically may want to predict the depth, you may want to predict some key points, you may want to predict the surface normals, and each of these different labels correspond to different tasks. Okay, and someone's asking me to talk a little bit slower, so I'll try to do that. The last question is, when might the loss function vary across tasks? So in both of these first two examples, the loss function is the same across tasks, and what's really differing is the data generating distribution. There's a few settings where we might see the loss function vary across tasks as well. One might be where we have kind of some labels that are discrete and some labels are continuous, and you may want to have different loss functions for different kinds of data, different kinds of labels. And the second scenario might be if you care about multiple different metrics of your performance. Maybe for your spam filter, you want it to be accurate, but you also, maybe you also want it to treat different emails in different ways. Maybe the way that it classifies spam and ham, you may want to kind of label things in different ways. Maybe another example of this is that we'll actually see in the real world example for recommendation systems is maybe you want it to be able to, maybe you have a metric that it cares about kind of user satisfaction, and another thing that cares about how long the user is paying attention to a video. Okay, any questions on these example problems?
Could you explain a little more about the per-language handwriting recognition? Are you trying to recognize handwriting for different characters for different languages at the same time?
Yeah, so what this looks like is you may, maybe you have characters written in Japanese and also in Arabic, like English language, and you want a network that can both kind of recognize both languages rather than a single system that can recognize just one of the languages. So in this case, you're going to have a different P of X and a different P of Y given X because the characters will look different and also the labels will be different. Maybe you'll have kind of an output of 0 to 25 for kind of English letters, and then maybe you'll have, I don't know, labels from 0 to a much larger number for Japanese characters.
Thank you.
Great. Do you have a question?
Just want to clarify one thing. I think everything on the right half of the slides look good, but on the left half, I just want to make sure I understand. For the task, Pi of X and Pi of Y given X, What are the examples for those? Like just to put those in perspective, like what was your scenario? What are these exactly?
Yeah, that's a good question. So pi of x. So this is essentially the distribution over inputs and the distribution of labels given inputs. And so in the example of Japanese characters, for example, there's typically you have some data of like handwritten Japanese characters, and p of x will be essentially the distribution that generates that data.
Oh, okay.
It's kind of the manifold of those images, and p of y given x is the kind of underlying, the function underlying whether a label, kind of a label given a certain input. Typically in practice, you don't actually have to deal with these generating distributions. You only deal with the data sets themselves. It's useful to think about the generating distributions though, because we assume that the train set and the test set are both drawn IID from those data generating distributions.
Okay, that makes sense. Thank you so much.
I have one more question. So in this multitask learning we are discussing here, does the model know which task it is currently performing, or does it make a prediction for all tasks?
Yeah, that's a good question. We'll get to that in like 1 or 2 slides.
Okay.
But typically the model is told what task it wants to do.
Quick follow-up question to that question. What's the function of the I in the PI given X? Is this for a specific training example?
Yeah, so the I is indexing, I'm just using that to index different tasks. So one task will have one index, another task will have another index. And I guess part of the reason why I mentioned that is in like multitask classification, for example, where Li is the same across tasks, then you could actually write a task as actually being pi of x, pi of y given x, and then just a single loss function that isn't indexed by I. So I'm just using it to index different tasks, and if something doesn't vary across tasks, then you don't actually need the index.
The multitask setup where we have different alphabets. Conceptually, why is that considered multitask? Why don't we treat it as simply, maybe instead of having an alphabet of 26 letters, we have an alphabet of, say, 50 letters where it's letters from both alphabets and a single data generated distribution and a single P y given x?
Yeah, that's a good question. So like we mentioned in the previous lecture, in multitask learning problems, you can typically always represent it as just a single task problem by taking the kind of the data set and having this be equal to, having a single data set be equal to the union of all of the individual data sets. And likewise as the kind of the loss function as the sum over the individual loss functions. So basically in all these situations, there is a way to kind of turn it into a single task learning problem. And as we'll see in the next few slides, there are scenarios where it's useful to treat it as a multitask learning problem by kind of changing the architecture, the network architecture in different ways, or leveraging the structure or changing the optimization.
So I think in the last lecture as well, you mentioned that it's either equivalent or at least faster or efficient to do it this way. I can see how this is more efficient, but I can see how this is faster, but is it always going to give us better results to train it individually, to train it all together versus training it individually?
Yeah, so we'll talk about this a bit later, but the short answer is that it depends on the application. There are some situations where it's actually better to treat these as separate tasks and train them completely independently. And there are other situations where it's helpful to train them all together.
Okay, thank you.
Do you still have a question, or did you just leave your hand up? Okay, great.
Can you unraise your hand?
I think you can lower your hand. I can also lower it for you.
Yes. Okay, I got it. Thank you.
Okay. Great. So Let's move on to the next slide. Actually, there's a question in the chat. Isn't multitask classification also multi-label learning? You could also view multitask classification as, in some ways, a form of multi-label learning. I wanted to special case multi-label learning because P of X is the same across tasks, whereas in multitask classification, it's typically not the same across tasks. Okay, great. So let's actually move on to how we go about training this model. So one thing that we typically assume for the different tasks, in addition to what we described before, is this notion of a task descriptor, which I'll denote with ZI. And we'll somehow condition the model. We'll feed the model this task descriptor as input. And this essentially tells the model what task it's trying to do. Now, and then the model becomes something that's actually conditioned on ZI. So for example, if we are again thinking about you're trying to figure out what paper, whether to accept a paper to review or not, maybe you're given the title of the paper and you want to know other things like you want to know the length of the paper, you want to know a summary of the paper, you maybe want the neural network to write the review for the paper as well so that you don't have to write it. Maybe these are the different tasks that you want to do. Then in this example, the task descriptor could correspond to a few different things. It could correspond to a one-hot encoding of the task index, which would essentially just be if the task index is 2, then it would be a vector that looks like this, where there's a 1 in a second location. If the task index was 3, then the 1 would be in the third position, and so forth. ZI could also be other metadata that you have. So, for example, in a personalization example where different tasks correspond to different users, then ZI might contain information or features or attributes of that user. It may also correspond to a language description of the task. So in this example that we talked about before, maybe a language description of each of these tasks might be, tell me how many pages the paper is, or give me a summary of the paper, or can you write a review of the paper? These would kind of give it some more structured information about what you're asking it to do. And this would also be similar to a question answering system, for example. And then it also may be some other more formal specifications of the task as well. And there are some applications where that may make sense. Okay.
Yeah, my question is regarding to the spam classification example. In the case of spam classification, the output space is the same for all the users, right? It's either spam or not spam. So when we are conditioning on the user's features, then wouldn't this resolve to a single task classification problem instead of a multitask classification problem? Because we are already conditioning on the features of the users, and the output space is the same.
Yeah, in many ways, when you do actually start conditioning on this task descriptor, it does kind of come to a single task learning problem. As we'll talk about in the next few slides, there's a number of design choices with regard to how do you incorporate this task descriptor into the problem, what sort of architecture do you use, and also alternative ways to optimize the model as well.
Thank you.
Hi, I'm wondering, for tasks like the identifying characters of different languages, I understand kind of the training set you can give a task descriptor saying, oh, this language is this language isn't. But how would you then go to an end result where you want it to detect the language and then classify the character?
Yeah, so if you want it to detect the language itself and you don't want to give it information about what language it is, then you could also choose not to condition on ZI. And in that setting, the architectures that we'll talk about in the following slides wouldn't necessarily apply because you want to detect what the task is itself, but some of the optimization techniques that we'll talk about would still apply.
Yeah, thank you.
Okay, so once you set up this architecture, then the vanilla objective that you're trying to optimize is what we talked about before, where you just take all of the loss functions for your individual tasks, sum them, and minimize the summed objective. And that's kind of, this is really like the basics. So like this is kind of all of multitask learning at the very basic level. Now, like I mentioned before, there's a lot of design decisions with regard to the model, the objective, and the optimization. For example, how should we condition on the task descriptor? What objective should we use? Is this vanilla objective the best option, or are there other good options? And also, how do we optimize our objective? So the vanilla option for optimization would be to use SGD or Atom, but there are also other somewhat delicate design choices there as well. Okay, so these are kind of the things that we'll talk about next. We'll talk about how the model should be conditioned on Z, and also what parameters of the model should be shared and not shared. We'll then talk about the objective and talk about the optimization. But first, let's talk about the model. So the model, the first question of the model is, how should the model be conditioned on the task? And let's first assume that Z is the one hot task index, like I had described before. So I have a question for you, which is, how should you condition on the task if you want the tasks to share as little information as possible? And if you want to give a shot at answering this question, please raise your hand.
Could you use the one hot index to branch off into separate neural networks for like each task? That would share as little as possible.
Yeah, exactly. So yeah, so if you basically want each of the tasks to share as little as possible, then what you could do is you can basically have 3 completely separate networks and use the one hot task identifier to basically choose which neural network, choose which branch you want it to output, and then do multiplicative gating, where you basically take each of the outputs of each of these independently trained neural networks with completely separate weights and pass that into this function here that basically iterates over each of the tasks and sees whether the task is the task indicated by Z and multiply that by the output. You could also do what we mentioned, which is basically have this gating happen at the beginning of the network as well, and either pass in all zeros, for example, and do basically have something like X equals the sum over the index over Z equals J times X into each of the networks. That would also be equivalent. And so one of the things that you'll note here is that if you take this architecture that gives you this Y as output, if you backpropagate into the network gradients and train the whole network for all of these tasks, maybe if your current task is task 2, then the gradients for all of these other branches will be 0 because of this gating right here. Any questions? Does that make sense?
My question is kind of related to the previous slide. So how do you weight across these multiple tasks? So suppose you have like each of the tasks don't have the same amount of data, for example, or some other issues. So how do you weight across these different tasks so that one task is not, hampering training on other ones?
Yeah, we'll talk about the weighting when we talk about the objective after we're done talking about the model. So just we'll talk about that soon.
Okay, thanks.
Hi, another question. So I see what you did here. It makes sense. My question is, what's the benefit of doing it this way? Because it feels like it wouldn't do that much better than the baseline of just one neural network trained on this task. Is maybe you want to ensemble like the outputs of all of them and have more heavily weight the one whose task matches our input task? I'm just trying to see how this is a little bit better.
Yeah, so this isn't necessarily something that you want to do. This is more kind of an illustrative example of how your choice of conditioning on Z connects to your choice of the architecture. So yeah, in general, this may not be something that you want to do. We'll talk about situations where when you may want to do this later, but in practice, you may want to share a lot more between the tasks.
Okay, okay. Thank you, Chelsea.
Great. I'm going to go through a couple more of the slides before going to the question, because I think that might maybe might answer some questions, but I'll get back to you in a few slides. Okay. Right. So this basically corresponds to independent training within like a single neural network architecture with no shared parameters. Okay. Now the other extreme that you could consider is one where you basically just add the Z, like concatenate it into the network at one point in the architecture. This could be at the beginning, this could be in the middle, towards the end. And if you simply just concatenate the Z with the activations at one of the layers, then basically all of the parameters of the network are shared. So this is kind of like the other extreme from what we talked about before. And I guess one thing worth noting is that if Z is still your one hot index, then technically also the parameters directly following Z will not be shared because if Z is a one hot vector and you're taking like your activations A and your one hot vector here, and you have say like 0, 1, 1, 0, then basically you then have a large matrix W right here. Then actually this is typically the other way around, but basically the half of the matrix W will contain either rows or columns, depending on how you put it, will contain task-specific parameters, because each of the parameters that are multiplied by this index right here will be specific to that task. But other than half of this W matrix, everything else in the network will have shared parameters. And so this kind of gives you a somewhat alternative architecture or alternative view on the multitask architecture, which is essentially think about, instead of thinking about conditioning on Z, think about your parameters and splitting those parameters into shared parameters and task-specific parameters. And if you do this, then you can write out your objective as something like this, where you have, again, your summation over tasks. And what this objective is doing is simply making it clear that task-specific parameters theta I are only going to be optimized with respect to the task, with respect to the objective Li, and they won't be optimized when you're using other loss functions. And it turns out that basically choosing how to condition on this task descriptor Zi is equivalent to choosing how and where to share parameters. Yeah, and the way that you can see this is if you take a kind of a simple architecture, say you have a simple architecture that looks like this, where you have a couple layers and then you split off into two different heads. We'll call this Y1 and Y2. Then you could consider basically each of the parameters here as your shared parameters, each of the parameters here as task-specific parameters for task 2, and likewise the parameters up here are going to be task-specific for task 1. This is kind of one way to view how and where to share parameters. You can also equivalently view this as a network that simply conditions on Z in a very particular multiplicative way, where you basically gate the two different outputs of this model. So for example, you set the prediction Y to be equal to Zi dotted with, maybe you call this A1 and A2, dotted with the vector A1 and A2. Okay. Looks like we have a few questions at this point. So do you have a question? Okay.
Yeah. I didn't clearly understand how the example that you gave maps to the conditioning on Z. Can you like elaborate more? How it maps to the model where we are like conditioning on Z at some point in the network?
Yeah, so in this architecture on the right, for example, this corresponds to one architecture where we're basically conditioning on ZI, and the way that we're conditioning on ZI is in a multiplicative way, where it's essentially gating which output you use, A1 or A2. So this architecture is essentially just one way to condition on ZI, where you have different branches of the architecture, and ZI is choosing which branch to use. And this architecture on the left is one way to view kind of the top point of view, where you have shared parameters and task-specific parameters. And I guess one thing in here is that on the right, it's kind of not clear that these are actually task-specific parameters that are only optimized for task 2. That's a little bit less view in this, a little bit less clear in this view, and a little bit more clear in the other view.
Can you explain again how gradient descent works with gating into different branches?
Yeah, so basically the objective here will correspond, you'll basically take this objective, compute the gradients, and you'll note that the gradient of this objective here is equal to basically the gradient with respect to the shared parameters and the task-specific parameters of loss 1, plus the gradient of the shared parameters and the task-specific parameters for task 2 of L2. Uh-oh. I think my pencil ran out of batteries. And so you compute these two gradients, and then when you run gradient descent, you're going to update the shared parameters using the sum of these two gradients, and you'll update the task-specific parameters with the first term and the second term separately. So the task-specific parameters for task 1 will only be updated by the first gradient, and the task-specific parameters for task 2 will only be updated with the second gradient here. In practice, with most deep learning libraries, they can basically handle this for you. They can figure out which, how each parameters will be updated, but it is useful to know kind of what's happening under the hood, that basically this, that for example, this kind of bottom layer right here is only going to be updated with regard to gradients from task 2. Cool, and then
what happens if I have, let's say, like overlapping data sets for the different tasks? So let's say that I have, task 1 is, detect some buildings or something. Sorry, I'm using my experience list. Like task 1 and task 2 have like slightly different data sets because, your labeling process may not be comprehensive for like all tasks that you want to do. In that situation, wouldn't the images or training examples that inhabit multiple data sets sort of have a disproportionate impact on the shared vector, on the shared component of the parameters? And how do you kind of deal with that?
Yeah, so to deal with that sort of thing, what you can do is when sampling the data, try and basically don't oversample, don't basically double sample for tasks that have shared data. So for example, one thing you could do is just sample from your data set as it is, and then backpropagate whatever losses you have for those data points. Although there is a bit of a trade-off there too, because if you do that, maybe if one task is overrepresented, then your other task will not get enough gradient data, and it's actually often quite useful to stratify your batches to have an equal amount of data for each task. So that's a trade-off to keep in mind.
Hi, I just wanted to do a quick logistic question. Could you post these annotated slides after the lectures?
We'll post the video, which will include the annotations. Unfortunately, Keynote doesn't save the annotations, but I can also try to look into how we might try to export the annotations afterwards.
Thanks.
Yes, please.
Okay, great. So we kind of went over the basics of conditioning. Now we'll talk about a few common choices of conditioning. So one choice that we talked about before was concatenation-based conditioning. where you take your input, you take some activations of the model, then you concatenate your ZI with the activations, or maybe you concatenate it with the input directly, and then you pass that through a neural network. So this is a very common choice. Another way that you could do this is with additive conditioning, where you take the conditioning representation, you maybe pass it through a linear layer or something to get something that's the size of your activations or the size of your input, and then you add that to the input. So these are kind of two choices. It turns out these first two choices are actually equivalent in terms of what the model expresses. I'm curious if anyone has thoughts on why concatenation and additive conditioning are equivalent. And if you have an idea, raise your hand.
Yeah, I think I can only have some idea from a very high level. I think from a very high level, both of these methods are just use the condition or the task descriptor Z as an additional feature.
Okay, so they're both using it as an additional feature. So that is, that's correct, but maybe there's a more specific answer. Do you have an idea?
Yeah, because in the second case, you pass the ZIs through a linear layer before adding them, so those weights could be implicitly also learned by the linear layer that you have in case one, in a section of that linear layer that is specific to the part of the full concatenated array that corresponds to ZIs. And when you add them in the output, you get the exact same thing.
Yeah, exactly. So kind of visually what this looks like is if you, you can essentially view this linear layer as the same as the weights of kind of half of this linear layer right here. And visually what this looks like is if you basically take the concatenated version and apply the fully connected layer or the linear layer right after that, what that looks like is taking this half of the matrix and applying that to the first half of the vector, which was the input, and taking this half of the weight matrix and applying that to the ZI right here. And so basically, when you apply this linear layer or this fully connected layer, you end up getting something. You end up getting this these two completely independent halves of that layer, and then you add them when doing the matrix vector multiplication to get the result. And so this addition right here basically is the same as the addition when you're adding right here. Okay, so this is something essentially to keep in mind with regard to the conditioning. There's also a few other architectures. So we briefly mentioned a multi-head architecture before, and that is something that's also a common choice for architecture, where you have some shared features that produce a shared representation of the input, and then you branch off into task-specific layers. Another choice is to use multiplicative conditioning, which we also talked a bit about before, where you take your ZI, you maybe pass it through a linear layer, or you directly multiply it with the input to produce the output. This would be like one layer of the network. And as we talked about before, there are kind of close relationships between multiplicative conditioning and branching, like multi-head architectures, when ZI corresponds to a one-hot vector and you're multiplying directly. And so, yeah, one reason why multiplicative might be a good idea is that for an individual layer, it's more expressive than simply adding or concatenating. Of course, at the neural network level, because neural networks are universal function approximators, it isn't necessarily going to be more expressive overall. They're probably both going to be equally expressive if you have a deep enough neural network. But for each individual layer, you do get more expressive power. And then, of course, it also is closely related to this gating and branching idea that we talked about before. So in some ways, multiplicative conditioning generalizes independent networks, independent heads, and so forth. Okay, let's go to a few of the questions. I'm going to assume that you had your hand up from before. Do you have a question, or is that also from before?
Yeah, the question is like 13.
Okay.
So here we are saying is equivalent, but in the second we don't have a linear layer after input, but in the then we're like here we
Yeah,
have
so
the
if you don't
linear
have a
layer.
Linear layer, then they're not quite equivalent.
I have a question in the same slide. So is it equivalent if you have a non-linearity as well?
If you also have a nonlinearity, then they're not like exactly equivalent, but depending on how that nonlinearity works, it may also still be able to represent the same thing.
Just to confirm, so if you have like a value, for example, then in one case, you might mask some negative things, and then when you add those, both the inputs will be negative, and so you have a zero overall. But when you concatenate them, you have two zeros in two different places, and depending on which, if both of them are not negative at the same time, then you have some.
Yes.
Yeah, so if you add values in different places, you won't get exactly the same architecture. I guess part of the reason why I was bringing this up is that this suggests that the expressive power of these two kinds of conditioning is very similar. Whereas when you move towards multiplicative conditioning, you get more expressive power than when you're adding or concatenating.
Can you actually can you explain why multiplicative conditioning is a generalization and has a stronger generalization?
So I'm not saying that it has a stronger generalization. I'm saying that the multiplicative conditioning, you can view it as kind of a more general way than simply forming independent networks and independent heads. So one instantiation of multiplicative conditioning produces this architecture, but multiplicative conditioning can also represent a wide range of other kinds of architectures and gating mechanisms as well.
But it doesn't
necessarily lead to better generalization.
Isn't it the other way around, that the multi-head is a better generalization of multiplicative? Because in multiplicative you lose the three signals and you just go to, they're all bundled into one. But in multi-head they're split into three different signals.
So a multiplicative conditioning architecture can represent this, I guess it kind of depends on where you put the multiplicative conditioning, but it can represent this exactly. But by nature of looking at this gating mechanism where you're basically taking Zi and dotting it with the output of each of these models.
Okay, I'll follow up looking for a snap question.
Sounds good.
Yeah, so I guess I was confused about why multiplicative conditioning will be more expressive per layer. Or if there's any intuition on that.
Yeah, I guess the intuition is that if you use additive conditioning at the individual layer, it can't represent multiplication. Whereas at the entire network level, it can represent that, because it could essentially, when you kind of, for example, if you concatenate things together, then the neural network, the next couple layers of the neural network can represent the multiplication function. But at the individual layer, the additive cannot represent multiplication. Does that answer your question?
Yeah, thank you. Yeah, I had a question about multi-head architecture as well as multiplicative conditioning. I'm not 100% sure how is multi-headed architecture a conditional architecture. Like, we are not specifically conditioning that on something, right? It will always output, it will always predict like three tasks, up to three tasks, right?
Yeah, so you can view it as a choice of conditioning, in the sense that if Zi equals is basically like 0, 0, 1, for example, you basically pass the input through all three heads and then gate it by this Zi right here. Then it will only give you the output of task C. If you basically have A1, A2, A3, dot, kind of take the dot product between this output and Zi, which is a form of multiplicative conditioning, then this will give you the corresponding output for the corresponding head.
Okay. And then in multiplicative conditioning, do we always have to select from one or the other, or can it be like a continuous function? Like instead of inputting one hot encoded values, one hot encoded vector,
Yeah, so
can
it
it
can
be?
be.
It can be continuous, and if you pass it through a linear layer, then that will allow it to represent a lot of other things beyond just the one hot vector.
Okay, thank you.
I'll take one more question from.
Hi, yeah, I had a question about attention. I can't really say I understand attention too well, but I was wondering if that's a way of implementing multiplicative conditioning, and also if that's a way of getting a more dense representation of the task information.
Yeah, that's a good question. Attention in many ways boils down to a dot product. So in that sense, it is a way to implement this dot product right here. Although I guess this isn't quite a dot product because it's actually just like a multiplication. There isn't a summation over the dimensions. I'm not sure. I haven't thought about that. I haven't given that too much thought. But you could view kind of a form of attention potentially as one way to condition as well. That segues nicely into the next slide, which is that there actually are a number of other more complex choices that you can think about with regard to conditioning or network architectures as well. Here's just a few of them. There are kind of a wide range of other approaches that the literature has produced as well. Often trying to target a specific domain like computer vision, or settings where you would expect to have kind of looking at relationships between objects or tasks or something like that. The other thing is that fortunately, the design choices of the architecture and conditioning are a lot like neural network architecture tuning in general, which is that they tend to be fairly problem dependent. They're often largely guided by intuition or domain-specific knowledge of the problem. And in many ways, they're, I think, currently more of an art than a science. So I presented kind of my scientific view on what the choices are and the expressive power of different choices. But in many ways, kind of beyond that, I think it tends to be a bit more of an art in designing these architectures. Okay, and this, so this kind of getting to the question in the chat about where do we actually concatenate the conditioning, this is kind of also a design decision that needs to be kind of chosen for the problem. And of course, when you're kind of designing architectures, you can use cross-validation to help guide your search as well. Okay, so that's it for the model. Now let's talk a bit about the objective. So we talked about the vanilla objective before, which is just the summation over all of the tasks. But often we want to weight different tasks differently. So we may want an objective that looks more like this, where there is a weight for each task. And you want to kind of upweight or downweight some tasks in various ways. Now the key question is now, how do you actually choose these task weights? One way to do it is just to manually choose the task weights based on what you find to work well, or based on some sort of priority if you care more about one task than another task. Unfortunately, manually isn't always a great choice because you have to, it's a manual process. So there's also a number of methods that have suggested ideas to actually adjust WI automatically. And they actually dynamically adjust them throughout training in order to lead to a better optimization or try to optimize things in a way depending on the application. So how do we actually kind of go about dynamically adjusting them throughout training? So there are various heuristics for doing this. So one heuristic that has been fairly popular in the literature is to encourage gradients to have similar magnitudes. This is what was proposed in this grad norm paper in 2018. And it's been fairly popular and seems to work fairly well, kind of guided by the intuition that if the gradients have similar magnitudes, then no one task will be dominating. But it's also a heuristic. So there are other approaches that are, I think, less heuristic and a bit more principled. one of these is to use task uncertainty. And this actually, I think, is a pretty interesting idea. I guess it's somewhat elegant in how this actually turns out. So this is a paper in 2018, and what they talked about is if you want to weight your different tasks differently, the intuition is that you may want to weight tasks that you're uncertain about higher so that you can try to decrease your uncertainty for those tasks. So the way that they formulated this is they assumed that you have basically a distribution of y given x for each task I, and they set this to be equal to a Gaussian distribution if you're doing regression with a mean that's equal to the output of your neural network, and a variance that is also a learned vector, and it's going to be a learned vector per task. And this is what's going to be your task uncertainty. And this is also what's called homoscedastic uncertainty, if you want to know a cool term. And this is in contrast to the typical uncertainty that you might have with a neural network that is kind of outputting a different uncertainty for each data point. That's what's known as heteroscedastic uncertainty. In this case, it's homoscedastic uncertainty in the sense that it's the same for all data points within a task, but it's going to be kind of representing the uncertainty for that specific task. That's why we have an index of I here. And this is going to be learned. And it turns out if you essentially minimize the log likelihood of your data points, or sorry, the negative log likelihood of each of your data points for each of the tasks, you can show that basically this objective is proportional to a sum over 1 over 2 sigma squared times Li plus log of sigma I. So what this is saying is that basically this corresponds exactly to Wi. And for tasks that you have a higher uncertainty because you have a higher standard deviation or a higher variance, you should you should weight those differently, essentially. Yeah, so if you have higher uncertainty, you should smaller uncertainty should lead to a higher task weight, and more uncertainty, you should actually have a smaller task weight. And I guess the thing that I find nice about this is that it actually kind of falls directly out of maximum likelihood training right here. Do you have a question?
Yeah, hi. I was wondering how we get the variance.
Yeah, so this term right here is actually learned. So it's just going to be a vector of learned parameters. So in addition to learning theta, and maybe I should actually have just written this here, in addition to learning theta, you're also going to be optimizing each of these variance vectors.
Sorry, it's the variance of like the weights or something, or?
It is the variance of this distribution right here. So this is a distribution over the label given the input. And the mean of this distribution is the output of this neural network, and the variance is given by sigma squared I. Does that make sense?
I'm still kind of lost, but I don't have a more precise question to ask for now.
Okay.
Yes. How do you know the data is on the labels are Gaussian?
Right. So in the paper, they also derive this for a cross entropy loss as well. This derivation is specific to using like regression problems for mean squared error, for example, or assuming a Gaussian distribution. But yeah, if you have discrete labels, then you can also derive a version of this as well.
Cool. Thank you.
Hey, so from what I understand, you're saying that if you just sort of have these learned weights, for your multiple task losses. That's you can understand that as being as putting some kind of Gaussian or as being some kind of Gaussian distribution for your P's, and that's how you can sort of theoretically derive the learn rate. Is that right?
Yeah.
Okay, good, thanks.
Hi, so I just want to make sure I understand. Basically, like on the high level, this makes sense, but where does what part of the equation is related to the variables that we have like the most uncertainty about? I'm trying to see where we see mathematically that those are weighted more.
Yeah, so actually I think I messed up the description a little bit here. So basically this task uncertainty, this is given by this kind of sigma squared variable.
That's the variance or the task uncertainty, or like that's basically equivalent in this case.
They're basically equivalent in this case. Yeah.
Okay.
So it's the variance over the data distribution of y given x.
All right. And then we see that it's weighted more where in the derivation?
So this is where I messed up my description. It's actually weighted less.
So weighted less. Okay, that makes more sense, and that's why it's logged, right, in the last equation.
That's why it's 1 over. It's 1 over.
Oh yes, 1/2. Yes. Okay, so, all right, that makes a little bit of sense. It's less weighted. Okay. All right. So as the variance increases, in this case, as the uncertainty increases, because we don't know what's going on there, we weight it a little bit less.
Yeah, exactly.
Okay. All right. I can roll with that. Thank you.
Yeah. Cool. Okay. Now I think I'm going to need to erase some of this to go on to the next point. Maybe I should find a better way to do this next time. So this is one way to produce the weights of your loss function. And this has actually been pretty successful in practice, and it's one that's it's a method that actually I've seen pretty strong performance now and used is a pretty strong baseline that people have used in a number of papers even now. Another approach for finding these weights was to instead take a perspective of multi-objective optimization and try to aim for monotonic improvement towards a Pareto optimal solution. And what I mean by this, I guess first I'll just kind of define what I mean by kind of Pareto optimal. And in particular, what this means is that first, a set of parameters will dominate another set of parameters if its loss is lower or equal to the loss of the other set of parameters for all of the tasks, and its overall objective is not equal. So basically what this is saying is that say you plot the negative loss for one task and the negative loss for another task. Ideally, you want to be kind of somewhere around here. That will lead to the lowest. That means that you have the lowest loss for both of the tasks. Then if you have one vector here, then that is theta b, then basically anything in this region right here will dominate theta b, including things that are on this line, and everything that's not in this region will not dominate theta b, sorry. So if theta a is somewhere over here, then that means that it dominates theta b. And the reason why I'm saying this is that you can define a theta as being Pareto optimal if there exists no other theta that dominates theta star. So basically, if you have a number of parameter vectors in different positions in your plot, maybe these are all the kind of parameter vectors that you are able to find, then the ones that are Pareto optimal are the ones that are basically on this curve, and this curve is what's called the Pareto front. And this is relevant because basically all the points that are, if you're at a Pareto optimal point, then that means that improving for one task will always require worsening the performance for another task. And so reaching a Pareto optimal solution is usually something that's good because it means that you've at least gotten to be optimal for one task, and with regard to that optimal, all the other tasks are at kind of a local maximum as well. Okay, and then the last thing that you could do for weighting tasks differently is to optimize for the worst case task class. And this looks like an objective like this, where you're optimizing over your parameters and taking the worst case I and only optimizing for that one. So this will basically take the task that's performing the worst and only optimize that loss. And the reason why this makes sense is that if you want to be kind of robust to the task that you might see at test time, if you imagine that you might be seeing kind of the worst case task at test time, then this is a good thing to do. Or this also connects to fairness. So if different tasks correspond to different groups of your population, then it might be best to optimize for the one that's doing the worst to try to ensure that they all reach some baseline level of performance. And so this has been used in like the distributional robustness literature and a range of other groups of literature as well. Okay.
Yeah, so I had a question for B and like I think also related to D point here. So for B, I didn't understand like if a task has higher uncertainty, wouldn't you want to train it more? And then relating to D, I think doesn't B go against B as in like in B we are trying to train tasks that we are certain about, whereas in B we are trying to train more on tasks that are not robust.
Yeah, so the kind of when you would use these different things depends on the application that you're considering. Task uncertainty corresponds to kind of a maximum likelihood objective, whereas this latter objective corresponds to kind of a robustness objective, which is just different. If you really care about all of your tasks, like treating them fairly, then optimizing for the worst case loss is one thing that makes more sense than trying to just maximize your likelihood. Whereas if you're in an application where fairness with regard to tasks doesn't necessarily matter that much and you just want to optimize overall performance, then one of these earlier approaches may make more sense.
Okay, thanks. Yeah, in the D optimized for the worst case loss, if you have a regression task, then sometimes it may just have numbers that are larger in magnitude. So is there any way of standardizing the loss such that they're all in the same ballpark? That's one question. And my second question is in the plots in green on the right, the left-hand side plot has negative L2 and negative L1. Is that intentional?
Yeah, this is intentional on the plots. Basically, I wanted it to be such that things away from the origin are better, and that makes it easier to see this this kind of curve.
The theta is not better than everything to the top and right? It's worse than everything to the top and right.
So the origin is you'd rather be at like one of these points than be at.
In the plot on the left, in the plot on the left, you have a theta and a vertical dotted and a horizontal dotted line. So that theta is worse than everything inside that dotted part, right?
Yeah.
Okay, thanks. Well, and what about the regression thing on part D?
Yeah, so you want to make sure that your losses are on similar scales, and if they're not, then this won't make sense and this won't work. And typically in like fairness applications, for example, you are optimizing the same objective for different groups.
Thank you.
Okay, I'm actually going to move on to the next slide just for time, because I want to make sure we get through the case study. Let's talk about optimization. So we'll really just to cover the basics here. When you have this objective, the approach that you might take to optimize it is to sample a mini batch of tasks from your set of tasks. If you have a relatively small number of tasks, then you may want to just sample all of the tasks. Then sample a mini batch of data points for each task. So you'll take the training data for that task and sample a mini batch from that data set. Then compute the loss for that mini batch using the loss function and using that mini batch. And then take the loss for the mini batch, for each of the mini batches, and backpropagate the loss into theta to compute the gradient. And then once you have the gradient, use your favorite neural network optimizer, such as Atom, to update your neural network. And what this does is that it essentially encourages your model to consider data from multiple different tasks at every mini batch. It ensures that the tasks are sampled uniformly, regardless of whether or not you have a lot more data for one task than for another task. And also, as was mentioned before, if you have a regression problem, it's good to make sure that your task labels are on the same scale. If they're not on the same scale, then you're essentially going to be putting a weight in front of the loss functions. That would be equivalent to upweighting the losses that have a larger scale. Okay, so that's the basics of optimizing. Now, a couple of the challenges that come up in multitask learning. One challenge is negative transfer. And what this means is that sometimes when you actually train tasks together in a single architecture, that actually performs worse than if you train independent networks. And so an example of this, if you look at a multitask version of the CFAR 100 benchmark, and you look at some recent approaches, training an independent network gets 67.7, and this actually does better than a model that only has one, that has basically a shared base and one task-specific fully connected layer. Also another kind of multi-head architecture does worse than independent training. And this kind of cross-stitch architecture, which is a fancier architecture, also does worse than independent training. So this is an example where we see negative transfer with these three architectures compared to an independent model. Why does this happen? This can happen for a few different reasons. It can happen for optimization challenges caused by kind of interference between different gradients. It's also maybe that different tasks may learn at different rates, and maybe one task learns a lot more quickly and uses up a lot of the capacity before the other task is being learned. It may also be an issue of limited representational capacity. It's often the case that multitask networks need more capacity than their single task counterpoints. This can also have to do with the optimization challenges before, because if you have a larger network, it may be easier to optimize. And changing these two things, increasing capacity, changing the optimization or changing the architecture in some way, can alleviate issues of negative transfer. And if you do have negative transfer, kind of the key thing that you can do is to share less across tasks. And of course, this also isn't just a binary decision. You can share more parameters, you can share less parameters, but there's also another thing you could do is to do soft parameter sharing. So you could have different task-specific parameters, theta I, and then encourage those task-specific parameters to be more similar to each other using a loss that looks like this, that it essentially minimizes the norm of the difference of those different task parameters. And this would be similar to basically taking two independently trained networks and encouraging the weights to be similar to one another through a loss that looks like this. So this is kind of another design choice that can go into your architecture. And kind of one rule of thumb is that if you're seeing negative transfer, then it can be helpful to share less, or use soft parameter sharing or have fewer parameters that are shared. This allows for soft parameter sharing, allows for more fluid degrees of parameter sharing, but it can be also yet another set of design decisions and hyperparameters. And in practice, I typically see hard parameter sharing used more than this form of soft parameter sharing. And then the second challenge that you might see is overfitting. And it may be that you're actually not sharing enough of the weights of your network. Multitask learning can be essentially viewed as a form of regularization where other tasks are regularizing the learning of learning another task. And so if you find that it seems like it's overfitting a lot, then it could actually be beneficial to share more of the parameters or put more weight on parameter sharing. Okay, do you have a question?
Yes, I understand how you talked about combining the losses of different tasks in the first lecture. But how do you combine different accuracies?
Right, so when you train neural networks, typically you use, if you have discrete labels, you typically use cross-entropy loss. rather than accuracy, because that's accuracy isn't really a differentiable metric.
When you have a multitask task, and you report a 67% accuracy, is that like average across the task? So is multitask itself a task?
Yeah, so the accuracy numbers that I was reporting for CFAR, that's averaged across the tasks.
Okay, thank you.
Oftentimes it's also useful just to report the individual task accuracies as well. Do you have a question?
Yeah, so the CFAR 100 example that you gave in the independent networks, did they just like train like 100 different networks for each kind of category? Is that what they were doing?
So in this case, it was actually 10 different tasks that corresponded to some of the higher level classes that are in the CFAR 100 data set. Yeah.
Got it, thank you.
Okay. Cool, so we're short on time, so I'm going to skip the break, but hopefully the questions have been a reasonable break, and let's go straight into the case study of real-world multitask learning, and then we probably won't get to the transfer learning, but we'll have an opportunity to cover that in a future lecture. So the case study that I'm going to cover is this paper that was came out in 2019. That's actually a paper describing a way to rank videos for serving them on as YouTube recommendations. And so the goal is basically to figure out what you want to show the user in this kind of part of the, I guess it's all this part of the side panel on YouTube for a given user. And they mentioned that there's a number of different conflicting objectives when making recommendations. They wanted to rate videos that, they wanted to kind of recommend videos that the users will rate highly, also videos that the users will share with other users, and also videos that the user will actually watch for a reasonable period of time. And another challenge that comes up is that there's also some amount of feedback. So the user may have also watched a video because it was recommended, and if it wasn't recommended, they wouldn't have watched that. And so this is also another challenge that comes up in these recommendation systems that makes it more difficult to leverage data when the recommendation system was actually in the loop of that data collection. This isn't a problem that they address in this work, but this is a problem that can be addressed with some of the reinforcement learning techniques that will be talked about, that we'll talk about later in the course. So the way that they set this up is the input is what the user is currently watching, the query video, and some set of user features for that user. And then with this input, they then generate a few hundred candidate videos. They then rank these candidate videos and then serve the top ranking videos to the user. The candidate videos, they pooled videos from multiple different candidate generation algorithms. This wasn't the focus of the paper. The focus of the paper was really the second step right here. Although the candidate generation process, different algorithms were like matching topics of the query video, looking at videos most frequently watched alongside the query video, and other algorithms. And then the ranking part was the central topic of this paper. So the ranking problem, again, kind of the input is the query video, also the candidate video that they're considering, and the user and the context features. And then the model output is some score that relates to engagement and satisfaction with the input candidate video. So engagement might be things like binary classification tasks, like clicks on the video, like numbers of clicks, regression tasks like the time spent watching the video, and satisfaction scores may be a binary classification task like predicting whether they would click like for that video, and also a regression task such as rating the video through a survey. And then they use a weighted combination of engagement and satisfaction predictions to produce a ranking score for that candidate video. And I found it interesting that actually the weights for this score were actually manually tuned for the algorithm to produce this corresponding ranking score. One question, we're maybe a little bit low on time, so maybe we won't discuss this right now, but I encourage you to think about whether this objective is reasonable for producing recommendations to a user, and what some of the issues what issues might come up with these kinds of metrics as well. This is, I think, is especially relevant right now because as kind of technologies really engaging people's attention more and more, this may not actually be a desirable outcome when there are other things that we want the user to spend their time on and their attention on. So I'd encourage you to think about this, and really to think about this when building any real-world machine learning system. Okay, the architecture, their kind of basic option was the multi-head architecture that we talked about before, where you have multiple bottom layers that are processing the input features in the embedding, and also a couple task-specific layers for engagement and the other metrics. And they found that this can harm learning when the correlation between different tasks is low, because they had like multiple different shared bottom layers that may not actually be good to share information between. So what they proposed in this work was to use a form of soft parameter sharing where they had a mixture of experts that was gated for different tasks. And basically what this corresponded to is they wanted to allow different parts of the network to specialize for different subtasks. So they have different expert neural networks that are written here. This architecture on the left shows two different expert layers, expert 1 and expert 2. They then decide which expert to use for a given input and a given task. So this is given by a softmax function, and then they compute features from the selected expert, and then eventually compute the output based off of what expert was used for which task, and also the features from that expert. And then in their experiments, they implemented this with TensorFlow on TPUs. They trained the models in temporal order as they got data. It turns out that you have a lot of data on YouTube, and so they were basically running training continuously to consume all of the newly arrived data. And then they kind of looked at offline metrics such as area under the curve and squared error metrics. They also did online A/B testing in comparison with the production system with live metrics, and in this setting, computational efficiency matters a lot. And the results, they found that with this mixture of experts, multi-gated mixture of experts model, they were seeing actually pretty significant increases in engagement and satisfaction based on the candidates that were ranked from this algorithm. And they also found that they were seeing kind of different experts used in diverse ways for different tasks. So for example, expert 7 was used a lot for satisfaction task 4, and expert 2 was used a lot for satisfaction task 2 and satisfaction task 3. Okay, cool. So that's kind of a real world example of a multitask learning system. To kind of respect your time, won't go through the transfer learning. We'll cover that in a future lecture. And I'll wrap up by saying, I guess we got through this first point, which is to understand some of the key design decisions when building multitask learning systems. And I'll leave you with a few reminders. For those of you that want to stick around, I'll continue to answer questions, but you're also, if you need to go, I understand that as well. And I'll see you on Monday.